general relativity step by step. Last time I had a vector and another vector, one with a contravariant index and one with a covariant index, and I was taking the sum of those, and I was talking about that as being v dot w, where one had a superscript and one had a subscript. What I'm going to ask now is, can we take a vector with contravariant components, and can we take it, I'm not sure what's happening here, there we go. Can we take this vector here with contravariant components and take v dot v equals what? We've not defined that yet. This is quite hard. It's not hard, it's just new. It needs new concepts. Well, let's have a think about this. That's vector v equals sigma vi ei, and I'm just going to take I equals 1 to 3, just a three-dimensional space, on the grounds that 2 is not enough and 4 is too many. We'll see later how I can generalize this to a four-dimensional Minkowski space, but for the moment we'll just stick to 3 dimensions. And I'm going to ask what v dot v is in component notation. Well, it's vi ei. Of course, you don't need to write the summation there. Dot vj, let's say ej. And I'm using different dummy indices, this I and that's a j and j, because I don't want to get tangled up. And of course that's summed over I and summed over j, vi bj ei dot ej. So let me just write that out in just in three-dimensional space. It's v1 v1 e1 dot e1 plus v1 v2 e1 dot e2. Quite a lot of work here. v1 v3 e1 dot e3 plus v1 v2 e1 dot e... no. It's row 2 column 1, row 2 column 1, plus dot 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 all the way down here to v3 v3 e3 dot e3. Well, that's great. So there's 9 terms there altogether, but of course if it was a four-dimensional space you'd have 16. So let's just think about this and how this crops up all the time. What we've got is v dot v equals sigma over I and j, vi vj ei dot ej. It's pretty clear to me that this is important. You see it all the time. So what I'm going to do is I'm going to define a quantity called g, and it's going to have a subscript I and a subscript j, and that equals by definition ei dot ej. Okay, and that's a definition of gij. Notice it is specific to a specific coordinate system. So for example, I might write, keeps on doing that, gij bar equal ei bar dot ej bar. Okay, so it's different in different coordinate systems. It's specific to the coordinate system, and it changes, gij changes to g bar ij with the coordinate system. Okay, so I'm going to think about this in a barred coordinate system, and I've got v dot v equals vi bar ei bar, that's a bit more neatly, ei bar, dot vj bar ej bar equals vi ei dot vj ej. That's in the barred coordinate system, and this is an unbarred coordinate system. All I've done is take my vector and I've just written it in an unbarred coordinate system, and so the components vi change and the basis vectors themselves change as well, but it's still the same vector, so this thing is equal to it. an unbarred coordinate system, which I'm going to say is Cartesian. This is a trick. It's not a trick, but it's a clever manipulative technique that we use over and over again. We've got this thing in a barred coordinate system. We don't know anything about it. It could be any weird curvilinear coordinates, could have circles and bars and all sorts of weird things. Of course, the example I'm going to choose is h and theta. And what I'm going to do is to transform it into something which I understand a lot better. Equals vi vj ei dot ej equals vi vj times ei dot ej, and this thing here, sorry, I should have expanded that in terms of gij, where gij is now the components of this thing g in Cartesian space. So gij is equal to 1 if I equals j, and 0 if I is not equal to j. Write that out a bit more neatly. Gij equals that. Because we know that in Cartesian space, E1 equals I, E2 equals j, and E3 equals k, where this is a nice orthogonal I, j, k system. Everything's at right angles, and everything's got unit vectors, so it's got this nice structure here. Equals the modulus of v squared, because it's equal to v dot v in regular Cartesian coordinates. Okay, that's quite important. Gij is called the metric, and I'm going to introduce this word tensor. I'm going to define it later on, but Gij for the moment is a quantity with two subscripts I and j. It's tied to a specific coordinate system, and it's called the metric tensor. Super, super, super important, and I'm going to talk about it in the next screencast.